So today, I want to talk to you about how to connect large fleet of battery-powered device, mainly Zephyr-based. So first, I would like to give you an overview of what is CoAP and discussing a bit some pieces of the protocols that are a bit misunderstood or that can be a bit tricky to get right. And also, more feedback of all the deployment I did in the past, because I work on cellular system and on more home automation system recently. And the way it works is a bit different. The way you implement the protocol and the trade-offs you need to do are a bit different. So I think it's interesting to talk about that. And and how you can use an open source solution to build that. Good. So first, a quick introduction to CoAP. So CoAP was created, I don't know, more than 10 years ago, no, maybe 14 years ago. So it was created for working with low power constrained networks. And because of that, it's an interesting protocol, because since they are targeting this very specific system for smart energy home automation with low power device and constrained networks, they did something a bit strange, I would say. It's not usual. We are used to a protocol where you have clear distinction between the reliability layer. For example, you use TCP on top of IP, for example, and then you have an application protocol on top of that. Here, for CoAP, they combine the two together, so the reliability layer and also the more application request response part of the protocol. So it's quite a compact protocol. You can use it on UDP, and it's ready done for a low power system. I will show you that later. But you can use it on something else, like UDP. You can use it on SMS, for example. I see people using it on top of serial line or even NFC. So it's not a generalist protocol. It's a protocol for a specific problem, which is wireless lossy networks. But you can adapt it to whatever you want if you want. It's not going to be very optimal, but it works. So the way it's encoded, it's binary, and it's very compact. But it's mixing the application part and the reliability part. I will show you that with an example. So I have a small ESP32 running Zephyr and the CoAP implementation of Zephyr here. Okay, so I'm connecting to my device. Okay, I need to connect to the Wi-Fi. Okay, I need to wait the device to be connected. So the device here is going to be the CoAP server. So it's going to expose resources that I will be able to use on my PC, which is going to be the CoAP client, a bit like HTTP server and an HTTP client. So for example, I'm going to show you what's going on. I need to type the right port. Okay. So on my machine, I'm going to use a CoAP client for getting a resource. So you use it a bit like HTTP. You want to get a value, I don't know. Oh, okay, so it doesn't exist. I get a 400 error. Or if I give a real URL, no, is that the typo? Yeah, I get a response. Quickly, without going too much into the details, and explain why CoAP can be confusing, because it's combining the reliability layer and the request response scheme in the same packets. So, for example, when I did the first get from the client, so I issue a get with this message ID, so 43634, and I have a token. So you have two identifiers. You have one, the message ID, and one which is a token. And you get a response with an error code, but with the same message ID and the same token. So the token is used to correlate the request and the response at the REST level, so the get and the response. And the message ID is for reliability. Basically, the first message is a confirmable message, so it's expecting a ACK for the same message ID. And you can see on the second one, I'm issuing a get, but the server is going to behave differently. It's going to first acknowledge the request to say, I received your message, you don't need to retransmit it. And then later send the content back, asking also a confirmation, an acknowledgement from the server. So in place of doing the transaction in 2 packets, here it's done in 4 packets. So yeah, it's due to the fact that you can decide how you want to handle the reliability of your message. If you want to take some time before building the response. And yeah, and that's why I find the CoAP a bit confusing. Yes, and then yeah, you find exactly what you can find with HTTP. So you can get URI, you receive response code, you have methods. So the goal of CoAP here is really to replace 2 protocols in one, so TCP and HTTP, and something compact and fitting low power networks and constrained devices. So that's why I say it's not a general purpose protocol like, I don't know, HTTP or MQTT. The goal of CoAP is really to target this kind of devices and application. Another feature is Blockwise transfer. So since you are using UDP, if your packet is larger than a UDP packet or the capability of the device, for example, if your device don't have a lot of memory, you don't want to send a 1 kilobyte payload, maybe you want to send a 200 or 500 payload. What CoAP is doing, which is a bit different of what TCP is doing, it's having a very simple approach to Blockwise transfer. So you send a first, for example, a first get for downloading something on the device. The device will send you back the first block and say, okay, this is the first block of N blocks. I have 20 more blocks to send to you. So then the client is going to iterate, ask the next block, get the block, etc., etc. So what is the main benefits? It's very simple. It's very simple to implement. The main drawback is as soon as you want to send megabytes, it's going to be very slow, especially if you have high latency. For example, if you have alpha seconds latency, which is common on this kind of network, every block we need a round trip of alpha second. And so if you need to move 1 megabyte, it's going to take a long time, which is different of what TCP is doing, because TCP has this concept of ACK windows, which is slowly opening, sending more and more packets in flight, in parallel, and optimizing a bit the bandwidth. So it's something to take
to take care with CoAP. If you want to transfer a lot of data, you need to be careful. It's going to take more time than TCP, for example. Quickly on the security, it's basically you need to use DTLS. You have another solution which is OSCore, but OSCore is not very popular. I will say there is not a lot of open source implementation. The main benefit of DTLS is that you need to do this uncheck, which is going, of course, to cost you time and bandwidth. But you have a nice protection against denial of service, but also you can support multiple cipher suite, and you are able to negotiate with the device different way to secure it. So you can have a system that is basically going to evolve from one cipher suite to another cipher suite later if you have a security issue. Now the quite ugly part of using a UDP protocol when you want to do something a bit more complicated than what I did. So what I did here is you have the CoAP server exposing the resources, the device, and you have the client which is going to issue requests to the device. When you want to start connecting this system to the cloud and not just interacting locally with maybe the device connected to the local network, it will take some the device to stop acting only as a server, but also acting as a client, sending, for example, a post to the server to send, I don't know, telemetry data or something. So when you do that, and in the middle of your internet connection, you have a router which is going to translate the public IP of the network into the private IP of your local network. It's going to put a session for the server to be able to send back packets back to the client. So the client sends a message, the server sends back a response. But if the server wants to send back a request to the client, it needs to do it in some given amount of time before the session is gone. And what is tricky is for TCP, most of the router you have in the wild, they keep session for more than 50 minutes. It's more hours than minutes. For UDP, because UDP is mostly used for DNS and voice over IP or conferences software or this kind of application, the timeout is very low. It's like 3 minutes normally, and sometimes as bad as 30 seconds. So you have basically, when a device sends a message to you, then you have a window of 30 seconds to send back requests and interacting with the device. And after 30 seconds, the device is not reachable. You need to wait for the device to come back. So, so it's where it's blurring the line with HTTP and this concept of CoAP server and CoAP client. Typically, when you want to connect this kind of devices to the cloud, you need to have the device acting as a CoAP client, posting some values to the server, and doing it regularly if you want to maintain a connection. Maybe you don't want to maintain a connection, it's not a problem. Maybe you will port the server once a day or something like that, which would be fine for a smart metering application. But if you want to maintain a connection, yeah, you need to send a packet regularly. And then, yeah, then the server is able to interact with the device, reading the resources on the device, rewriting resources on the device, for example, for reconfiguring the device or interacting with the device. Yes, so it's a tricky problem. So for example, for home automation style application, since you don't really control the network, you don't really control what kind of internet service providers the end user is going to use, what kind of Wi-Fi router. Maybe they pile up 2 Wi-Fi routers. you can imagine all the complexity of that. So you need to use either keep alive, so having the device pushing data all the time to keep the device, the server, and the device connected and be able to send back packets to the device. Typically with this kind of application, for example, if you have a phone application connected to the server, and you want to interact in real time with the device, you have no choice. You need to keep the connection open. Or if you don't have the needs for this kind of interaction, you can buffer the operation of the cloud and wait for the next polling from the device. So that's one network topology where CoAP is used. So it's not a problem. It's not a problem. It works to do this for this kind of low power network like 6LoWPAN or Matter thread, because it's a local area network. You refresh always the connection anyway every 3 seconds. So it's not going to add a lot of battery usage on your device. But for cellular-based application, where you use a 4G low-power modem, for example, it's a bit complicated because every packet costs you a lot. So it's not practical to send a message every 30 seconds. But you can use different solutions. So either, you use some queuing system and you say my device is just going to poll from time to time and I'm not going to maintain a connection. You can maybe try to use the good old SMS for forcing the device to reconnect when you want to interact with the device. It's a bit tricky to secure, but it works. Or you can ask your connectivity provider, your mobile network operator, or the people who are selling you a SIM card, to create a private network for you. So it's a software-defined network they build on top of the public network. And in this private network, you will be able to select your IP address and remove totally the NAT from the picture. So you will not have anymore the problem of the NAT timeout. You can also try to use TCP-based system if you can handle the performance issue which come with using TCP on this kind of lossy network. Obviously the right solution would be IPv6 in both cases, but we are not there yet. One word about lightweight M2M. So lightweight M2M is a device management standard built on top of CoAP. So on top of CoAP, you have CoAP, this REST interaction between a client and the server, sending get, put, post, and being able to do modification or downloading content. So on top of that, they build a device management system where you can keep alive the device connected using what they call registration, provision the device, and also a REST model for management objects, which are standardized. You have a very specific object for describing the device. You need to populate your device data in the device object, and then it's going to be interoperable. I can maybe quickly show you how it's looking in practice. Okay, I'm connected. Wow. Is it working? Okay, so this is open source lightweight M2M server. So you can see you have devices registering with the server. And then when you look at the device, you have URL on the device for different objects, and the objects are standardized. For example, the device object is looking like that. You have all the information you need to populate if you want to conform with the standard. For connectivity monitoring, it's a bit the same. you do a read. So as you can see, the read is very slow, well, very slow. It's taking 2 seconds because this is an NB-IoT device. Oh, it's gone. Let me check. Yeah, no, it's back. Yeah, you can see the read. It's taking quite a lot of time. It's the time for NB-IoT network to send a packet, then get back the response. So it's not bad. You are in good coverage, but it can be worse than that. Okay, so. Okay, now a bit of feedback from deploying this kind of technology at scale. First, when you really want to use CoAP. So using CoAP on a Zephyr device is very easy because you have everything ready in the project. You have a CoAP client, a CoAP server, even lightweight M2M, you have everything ready. But then you don't want to use in every case. You want to use it when you have a constrained network. When I say constrained network is something like cellular, NB-IoT, thread matter, where you have high latency, sometimes high packet loss, or if you want to have some kind of reliability on cellular network where when you are in fringe coverage in bad condition. For example, LTE-M, which is another low power 4G, works well with TCP, but as soon as you are far of the cellular tower and you are in bad condition, TCP is not working anymore, but CoAP can work. So that's one of the benefits of CoAP. When you want to use lightweight M2M, so lightweight M2M, as I show you, you need to fit into the standard. So it's always a bit complicated. So you probably want to use that if you have a need for interoperability, if you want your device to be able to be managed by different vendors which are supporting the standard, or simply if you need the standard compliance. For example, most of the cellular devices, they have a lightweight M2M client because it's used by the mobile network operator to be able to monitor and reconfigure some capabilities of the device. Or if you have strong security requirements, that could be interesting to reuse lightweight M2M because they have everything ready to provision, certificate, bootstrap the device, put in place key rotation, provisioning certificate on small devices is always a bit complicated. Or for example, if you need to connect to multiple servers and manage access control list between the different servers, that would be interesting to reuse lightweight M2M. But you need to fit in the standard, and it's sometimes a bit complicated, especially with battery-powered device, low-power devices. I work with a customer which built a very constrained system, a tracker, a package tracker, and the system was really just an antenna, a chipset, and a battery, a small battery, and the system was designed to just last the time of the parcel to go to its destination. They started to use lightweight M2M, but lightweight M2M was not exactly fitting their needs because in lightweight M2M you need to send a packet for register the device, send a packet for sending the telemetry data. So it's 2 packets. So it was consuming more battery than creating something ad hoc with CoAP and packaging the 2 together. So they first started with lightweight M2M, and then finally they made the trade-off to give up on the interoperability and move to something proprietary to save some battery. So yeah, it's nice to have interoperability, but for low-power devices, it can be a huge constraint. Another Another thing that is interesting with CoAP is you are able to do firmware update with very constrained devices on this kind of constrained networks. But you need to be a bit careful. You cannot just try to send your firmware image from the server to the device because the connection is not great. If the device reboot or the connection break, you will not be able to resume. So maybe you will start from the beginning, draining more and more battery from the device. So what you probably want to do is to first send a URL to the device and let the device download the firmware. When, for example, the device is having battery or the user is not using the device, and let the device deal with it, start downloading, resume if needed, so you can really optimize your system. Another interesting question with the deployment of those devices, those low power devices at scale, is that you often, it depends on the business model you have, but for example, if you are building cheap hardware, you sell the hardware, and you don't have a very strong revenues from subscription from the end user. It's difficult to build your system with software as a service that are costing you every month. But also maybe it's also expensive to do it everything yourself. But at the end, since it's a low power device, you will need to optimize a lot of elements, but also the first firmware you will ship will always have some bugs, especially bugs at the lowest level of the communication. And even if you can release a new firmware, the factory, the warehouse will still contain those old firmware with all those old bugs. And you are basically forced to support those bugs for the lifetime of the device, so it could be 10 years. So it could be a bit complicated to do that with proprietary system. Open source gives you a lot of more control on, typically on the server side. Maybe you have one version of the device which behaves strangely. You have a workaround for that, and you will keep the workaround until the device is not supported anymore. So that's why it's interesting to look at open source solution, because you can always fork and maintain your own workaround for managing your mistake from the past, in place of trying to force your software vendor to do it for you. Okay, so to start using CoAP. So on Zephyr, it's very simple because you have a CoAP client, a CoAP server sample. You have also a lightweight M2M client in Zephyr, which are good qualities, are working out of the box. It's not very simple to understand how to use the CoAP client and server with DTLS for securing the communication, and also how to use the CoAP stack in the client plus server mode, like the device posting element, but also receiving requests from the server. But the lightweight M2M client is doing that. So if you are looking, for example, look in the lightweight M2M client. One of the other interesting constraints, if you want to create a Matter device and you are targeting a certification, you probably want to use whatever thread implementation is provided by your silicon vendor. So most of the time it's OpenThread. OpenThread is containing a CoAP client. So you probably want to use this one and not use in parallel of the CoAP clients, the other CoAP client, which is in Zephyr. And of course they have different APIs, so they are not very easy to switch over. And if you are not using Zephyr, if you are using Linux, for example, libCoAP is pretty good. It's probably one of the most complete CoAP implementation. On the server, you have basically two options. Either you use Java, and in Java you have Eclipse Californium, Open CoAP, which is a bit more recent, I would say, or modern, a bit easier to understand. Eclipse Californium is probably old. It's older, but it's more battle tested, and yeah, and it's a bit more well known. And yeah, if you want to use lightweight M2M, you can start with Eclipse Leshan, which is pretty complete from a lightweight M2M point of view. Or you use Go. Go, they have a nice CoAP library with a DTS implementation. All those libraries are working very well at large scale. They are deployed by vendors at large scale. But outside of Java and Go, you don't have a lot of options. The other libraries are not very great, or they don't really exist. That's good. That's it for me. Just to say that Tado is hiring in EU, if you are interested. Yeah, that's it. Thank you. And we have time for questions, if there is questions.
So I was wondering, one of the parts of the presentation that interests me the most is how to get to the client from the server. And you mentioned a few strategies. SMS was one of them, which surprised me quite a bit. I'm wondering, in constrained environments like that, the two constrained environments that you define, which is battery-powered device but in the home, and battery-powered device but connected via cellular, NB-IoT or LTE-M. What's the as per your understanding, the most common approach to use to get, for example, in the firmware update diagram that you had the initial push from the server to the client of the URL, right? That needs to happen, so that needs to go through the NAT, right?
Yeah.
So what's the most common approach?
The most common approach is to do that is to have the device polling the server to say, hey, I'm here. And then once you have the device connected, then you can do sending the firmware update.
Okay. So not going beyond the threshold of the 30-second threshold or whatever.
Yeah.
Okay.
In practice, you never connect to a device from an IP address or over the internet, maybe locally on the local network, but from the cloud to the device, you never try to reach an IP address. You need to wait for the device to connect. Maybe the device will keep the connection for weeks open for you. And then, yeah, you can send a message, so firmware update.
So then on the server side, basically you have, say, a firmware update, you have it queued, and as the next time the device connects, that's when you do the post to the device. Okay, good. Thanks.
And do you have experience with Eclipse Leshan in production environment and production deployments?
Yeah, basically I funded the Eclipse Leshan project, and I use Eclipse Leshan for large-scale deployment.
How large?
Millions.
Okay, great, thanks.
Even if it's not out of the box. It's basically my job to help people to scale this kind of open source solution. Because, for example, Leshan, it's coming with a nice sandbox demo you have. Well, it's what I showed you. But it's working on single node. If you want to make that running on multiple nodes at scale with security, it's a bit more complicated. But you can do it. The base lightweight M2M implementation is scalable.
I was wondering if you had much experience with like access control and authorization from clients accessing. So, for example, like a client, specific clients only being able to access certain firmware binaries or things like that, if you had experience doing that?
Yeah, very small one, like for lightweight M2M, you can have a device connecting to registering, so doing this kind of dense refreshing to 2 servers. For example, one was just in charge of managing the firmware update. So in the device, it's configured that this firmware update object resource is only accessible by this server. And the rest of the resources, so like the sensor and everything, was configured to be managed by a second server. That means that you need to connect to 2 servers. You need to maintain two CoAP contexts, 2 DTLS contexts, so it's quite costly on the device, but it works. It's a bit tricky. The standard is not very clear about how to do it, but yeah, you can do it. Thank you.